Okay, this is QQT number 4. It looks like we have a block sliding down a ramp and then off a tabletop. Okay, so my initial thought is we might be looking at some energy conservation here. And then off the table, we might be looking at some projectile motion, which means I need to look at X and Y direction separately. Okay, and I need to remember that the time of flight comes from that Y direction. Okay, so I have a student releasing a block of mass M from rest at the top of a table. The block moves down the slide off the end of a table, height 2, landing on the floor over a horizontal distance d from the edge of a table. Friction and air resistance are negligible. The overall height of the setup is determined by the height of the room. Therefore, H1 is increased, H2 is decreased by the same amount, so that the sum of H1 plus H2 equals H. Okay, so the student wants to adjust H1 and H2 to make D as large as possible. So without using equations, this was part A, explain why making H1 very small would cause D to be small, even though H2 is large. Okay, so H1 is this part up here, and that's the part that I've talked about energy conservation. So how would having a small H1 in terms of energy conservation lead to a small distance? Well, let's see. So if H1 was really small, then this change in gravitational potential energy would be small, which means we have a really small velocity coming off of the table. Okay. Now, even though H2 would be large, which means we have a large time of flight, if you have a small velocity, this distance is still going to be small. Okay, so that's my explanation. So if H1 was small, the change in potential energy of the block over H1 would be small, leading to a small kinetic energy gain and a small horizontal velocity off the table. Because it says we need to mention H2 and why the distance is small. So having a large H2 does give more time in the air, but with a small horizontal velocity, the horizontal distance will still be small. Okay. So explain without using equations why making H2 very small would cause D to be small, even though H1 would be large. Okay, so I'm kind of going to explain the opposite of what I just said. So I'm going to say if H1 was large, the change in potential energy would be large over H1, leading to a large gain in KE and a large horizontal velocity at P. However, if H2 is small, the time in the air is small, So even with a large Vx, the horizontal distance dx is still small. Okay, so essentially the same thing twice, just opposite. Let's check my scores for that. So part A1, I get 1 point for recognizing the small horizontal velocity and for implying that the block doesn't go very far, even if there's a longer time of flight. I did that. Part 2, for recognizing the large horizontal velocity, but a short time. Okay, so I need both of those things, the information about the horizontal velocity and the time of flight for both A1 and A2 to get full 4-point credit. Okay. So the formatting here got kind of weird. B is derive an equation. C1 and C2 are explained. Okay. So B, derive an equation for D in terms of H1, H2, M, and physical constants as appropriate. Okay. So let's work backwards. In the x direction, the one and only equation I can use is x equals vt, where this v is the velocity in the x direction. So in order to get the horizontal distance traveled, I need to know the velocity in the x direction and the time of flight. Well, how am I going to get the time of flight? I'm going to use the y direction. Now, this is projected horizontally off the table, which means my initial y velocity is 0. My acceleration is going to be equal to negative g. The change in height is going to be h2, and I'm looking for the time. Okay. So that means I'm going to continue the equation up here since I already have it written partially. Okay. That means the only equation I can use to help me find the time of flight in the y direction is y equals y0 plus v0t plus 1f a t squared. Okay. So this is 0, this is 0. Y, I'm falling, so this is negative h2 is 1/2 negative gt squared. Okay. So I'm going to multiply both sides by 2, then divide by negative g, so I get h2, 2h2 over g is t squared. So the time is the square root of 2h2 over g. Okay. So x is vx square root 2h2 over g. All right, so now in order to find that distance, I also need to know this horizontal velocity. The horizontal velocity comes from the energy conservation that occurs on that upper part of the ramp. So initially, we start with gravitational potential energy, and I'm going to set my 0 height here, and we end with kinetic energy. Okay, so we start with mg. The change in height, or the height above 0, is h1. Now you might be thinking, Narc, why aren't you using the ground? Well, because I want to find the speed at this location, at this tabletop height. Since I want to find the speed at that tabletop height, it doesn't make sense for me to use the ground as 0. I should use that tabletop height as 0. Okay, so if mgh1 equals, hold on, it's not letting me write for some reason. I can erase, but I can't write. Hello? Ah, there we go. Okay, so I have mgh1 equals 1/2 mv squared. Okay. So my masses cancel. Wonderful. And remember, this v is the velocity at this point P, that horizontal part. So I have 2g h1 is v squared. So vx at point P, square root of 2g h1. So now I can take that vx and substitute it in here. So x is square root of 2g h1, square root of 2h2 over g. Now, I'm going to combine, since these are both square roots, I can combine everything under one square root. So I can 2g H1 to H2 over G. And that shows me that the G's cancel. And this becomes square root of 4 H1, H2. Now, you might be thinking that that looks weird, but let's think units-wise. H1 and H2 both have units of meters. So that means under the square root, we have a meter squared. Well, the square root of a meter squared is a meter, which is this horizontal distance. Okay. So this actually took like 3 different equations. I needed 1 to find the time of flight, 2 to find the horizontal energy, and 3 to put it all together to find the horizontal distance. Okay. So let's see if I get all those points. So I get 1 point for using energy conservation, 1 point for setting up a time of flight, 1 point for using D equals VT. So their final equation is pretty much exactly what I have. They just took the 4 that was under the radical and simplified it to make it 2 out front. Okay, so I got all 3 of those points. Yay! Now the fun part. So part C wants us to explain or what equation or step shows that or supports your reasoning for part A1. So part A1 we talked about if H1 was small, the change in potential energy would be small, so we'd have a small kinetic energy. So which would lead to, less speed would lead to less distance. So the energy conservation equation shows that a small H1 would lead to a small Vx. Okay, so there's a small horizontal, a small Vx, which would lead to a small horizontal distance, D, even with a large time. Okay. So in part C2 or A2, we really talked about how H2 being small leads to a small time of flight. Okay, so let's talk about the time of flight equation. So the time of flight equation, and you could certainly rewrite it, T equals 2H2 over G, shows that a small H2 will yield a small time of flight leading to a small D, even with a larger Vx. Okay, let's see how I did with C, with those 2 answers. Wherever C is. Okay. C is all the way down here. Okay, so C1 I get mentioning correct equation or step of reasoning, energy conservation, and why it supports it. So they say my energy conservation reasoning mirrors my reasoning that a small ramp height corresponds to low potential energy, which converted to low kinetic energy, hence low speed. I talked about that, so I got those 2 points. Part C2, I get 2 points for mentioning the correct step or reasoning, time of flight, for correctly explaining why. So they say the time of flight calculation shows that T is proportional to square root of H2, so smaller falling time H2 corresponds to smaller time of flight. I got all those points. Yay! Okay. So let's take a look at question D, which is the last part. So D says, if the experiment is repeated on the moon without changing H1 or H2, the new landing distance D be greater than less than are the same as the landing distance when performed. So our landing distance, remember, was the square root of 4 h1 h2. Now, the only thing that's changing on the moon is the acceleration due to gravity, but the acceleration due to gravity isn't in that equation anywhere, so this answer is going to be the same. So we can say essentially what I just said in my explanation. So the equation for D does not depend on acceleration due to gravity, which is the only change on the moon. So D remains the same. Oops, it'd be great if I finished spelling out words. Okay, so because G is not in the equation, G is not going to affect our answer, and that's why it is the same as. Let's check my points for that. All the way down at the bottom. So I get 1 point for reasoning that is consistent with the functional dependence of part B. So basically, you could get this question right even if your equation was wrong, as long as you answered based on your equation. Okay, but really, it should be the same as, okay? And your reasoning should be that distance does not depend on G, so doing the experiment on the moon instead of Earth makes no difference. Okay. And that is the end for this QQT number 4. I hope that you have a wonderful rest of your day.